So, we will start the new topic now. So, route to turbulence, how does turbulence occur in fluids? So, I will show you how things go, but only sketch it. I mean, it is a very wide topic, but I will take some examples and show you how it happens for some systems. And some of these problems are still unsolved. People really do not know turbulence, how does it occur in pipes, a simple pipe flow, it is not understood. But the example which I will show you are somewhat better understood, like convection is the example which I am going to show you. Okay. So, first will be instability. So, in fact, this instability is very similar to what happens for pendulum. Pendulum standing up is unstable, it just falls. If you make any perturbation, it falls. So, same thing happens for fluids until some for parameter below certain values, it is stable. There is no fluid motion, or fluid motion is very ordered, but if you increase the parameter a bit, then fluctuation starts to grow. So, fluctuation must grow, that is instability. Okay. But you see, in real life system things cannot grow to infinity, this is actually exponential growth. In pendulum, of course, theta grows, but it is bounded by, it cannot go above this pi. Similarly, here there is a bounding, there is a bound on the growth, and that happens by nonlinear saturation. In fact, the nonlinear terms, so this instability, I must say, this is a linear stability. So, in this course I am going to do only linear stability. There are something called nonlinear stability, but we will not do that. Okay. But so, here the equation will be linear, but after some time the nonlinearity takes over and the growth saturates. So, you could get a fixed solution, or you could get some oscillatory solution, and then after this, if you increase the nonlinearity further, then you will get more patterns, chaos. So, it is just that how much nonlinearity you put in. By the way, if you put more nonlinearity, you may get a better pattern. Okay. So, this is a nonlinear system. I showed you the example. I put in more nonlinearity, I was getting a stable solution. So, nonlinearity is not more nonlinearity, more disorder does not mean that. Okay. Nonlinearity is complicated. After that, we get patterns and chaos, and after that comes turbulence. Okay. So, I will just illustrate by some examples, and some of it you will do it as a project. So, first let us set up an equation, let us set up a system which will work as a framework. Okay. I will not derive the full equation, but I will follow this convection example. So, the idea is that we have a hot plate below, hot plate is a plate, and cold plate above. So, it is not like heating in a kitchen where the top lid is open typically, right. But here water is full and I close the top lid. So, is that so this is full fluid. So, this is an approximation, because you do not want air in between, air bubbles. So, all that simplification happens as a result, and gravity is acting down. So, you see there is a mean temperature. If there is no convection, convection means the velocity field will start to turn around, right, like this is the convection rules. But if there is no convection, then temperature will drop linearly. It is a conduction solution. So, kappa grad square T is 0. Diffusion equation, you turn off d by dt, and the solution in 1D is T is linear in Z. Okay. So, this is my system. So, I need to set up my equations. So, this is called, we make some assumptions which I will not delve into it right now. So, we assume that my conduction profile, this is T bar means mean profile. Mean profile is linear, T bar. So, this mean is coming because my boundary condition, my bottom is hot, top is cold. Now, when the convection is not present, so my temperature is just this, but when convection starts, there will be fluctuations in temperature, right, because some place becomes more hot and cold, from this mean. So, there will be total temperature will be deviated from this, and so we denote, we follow notation that after convection, okay, this when convection has started. So, this fluctuation is added to that. So, if theta is 0, that means no convection, theta is non-zero means convection, and instability will happen when theta grows exponentially in time. Okay, so, that is the solution we are looking at, that is instability. Okay, so, the equations which I will follow. So, this I am not deriving it. So, only new term I am adding is this, right. We have seen this is a pressure gradient by density, this viscous term, nonlinear term and acceleration. So, what is this alpha? Alpha is thermal expansion coefficient. G is exertion due to gravity. And theta is temperature fluctuation. Huh? So, I have absorbed the mean in this sigma I am not using as pressure. So, sigma is more than pressure, all this T bar and so on have been absorbed here. But if you are interested, read it, but if you are not quite keen, just follow the mathematics. Okay, that is what I would recommend, because it is a field on its own, and this is covered in the other book. So, this convection book, a buoyancy driven flow. Okay. Now, this is one equation for velocity field, and I have, so I need one more equation, right, for temperature. So, we put another equation for temperature. So, this is d by, so this total temperature derivative d theta by dt, and this is that gradient part which comes in derivation, okay, and this is a diffusion part. And we still assume that del dot E is 0. This is slightly surprising, right, because it implies that density is constant. If density is constant, then my buoyancy will stop, but I want hotter fluid to be lighter. So, it turns out that this is to first order approximation. So, variation in density is non-zero, but that occurs only here, and that is higher order, and but this assumption can still be made for simplification. This is an assumption, and this is called Boustett's approximation. This approximation is not good for sun, also for earth it is not excellent, but it is okay. This is not correct, okay, but we will not delve into this. Okay. So, we treat this as equation, and it is a good equation for convection in the kitchen, but not for the solar convection. So, for atmosphere this is a good equation. Okay. So, any questions on this? I mean, there will be lots of questions, but I mean you understand each term. So, this is a buoyancy term. So, buoyancy is feeding the velocity. So, system will become unstable because there is something is giving energy, right. Somebody is exciting you, that is why you become unstable, somebody is go fight. So, that is what is going to happen. So, this is giving energy, and if there is significant energy, then the roll starts to form. Okay. So, you non-dimensionalize this. So, this non-dimensionalization is slightly different than what I told you before. So, for Navier-Stokes, standard thing is mean velocity field far away, that is used as velocity scale. Cylinder or box size uses length scale. Here we make slightly different assumption. So, we make d, the box size is still uses the length scale, this d, but my velocity scale is kappa by d. So, kappa is thermal diffusivity. So, kappa by d has dimension of velocity. Okay. So, this one scale, there are different types of scaling, but I am going to use for my lectures this scaling is simplest. So, it is not u naught. So, I am not using the velocity field which is going like this. Kappa by d is assumed is one scale. Is that okay? So, you can choose your velocity field in different ways. Now, if I use that, I can of course find time. What is time scale? T naught will be L by d by u naught, d by kappa by d. So, d squared by kappa, okay, straight. So, we can also find pressure scale. So, if you plug that in, you get this equation. Now, there are two parameters, Rayleigh and Prandtl. So, this Rayleigh is, so this is a non-dimensional equation, okay. So, all the terms are non-dimensional. That means it has no dimension, no centimeter per second. So, these guys also must be non-dimensional. So, Rayleigh is, this is called Rayleigh number. And it is alpha g d cube delta. I use delta as a temperature difference between the plates. So, delta is T bottom minus T top. Okay, so I did not want to use, many people may use delta T, but then I need a bracket. So, I just use that. And nu is kinematic viscosity and kappa is thermal diffusivity. And what is Prandtl number? PR is nu by kappa. So, this is called Prandtl number. Okay. So, we will work with these equations under the assumption that delta u is 0. So, it is still incompressible except this buoyancy term. So, I can use Cray-Herring, right, with this, because I have delta u is 0. So, we can use Cray-Herring. Okay, so, this is the system which I will work. Now, so this is called thermal convection. Okay, this equation for thermal convection. Now, we will do two more systems. I will include rotation in it. So, this becomes rotating convection. Okay. Then you turn off the rotation and put in magnetic field. So, that is magnetoconvection. Okay. So, I will set it up, but I am not going to tell you the physics behind it. The equations will treat them as equations, and I will tell you why they come, but not in full detail. Okay. Rotation is easy, rotation is just Coriolis force, centrifugal force is absorbed in pressure, but magnetic convection, the terms are more complicated. Okay. So, I will start the instability calculation for thermal convection. Okay. I will show you how the roles will start coming in, and that happens because of the buoyancy. So, the physics idea, so I am heating from the bottom. So, light fluid is trying to go up and heavy fluid is trying to go down. So, that is feeding energy to the system, but viscosity is not wanting it to go. The viscous term damping, so well, why are you wanting to go? So, they are trying to slow it down, but when the temperature is strong enough, it wins over the viscous term and it just grows. So, as I said, I am working with linear instability. So, you must turn off the nonlinear term and see whether a linear system gives you stability. Whether not every system gives instability. So, gravity waves. So, in fact, it is connected to that this problem. In the ocean, we have there is a gravity, so which tries to pull down. It is a stable system, and we get wave solution. It is not unstable. In the linear regime, it only gives you wave solution. Wave is stable. They move, but it does not grow in time. Okay. So, first we need to linearize our system. So, this is the equation which I just wrote. So, this term and this term are making the system unstable. Okay. So, I am telling you, this is like buoyancy, giving buoyancy, and this term is coming because of the gradient. Now, I want to make it linear. So, which are the nonlinear terms in this equation? So, this term nonlinear means quadratic terms. or higher order, and you don't get theta. So both u and theta are variables, so you drop them and you need to retain all three, all other terms. This you should retain. So this is my linearized equation, and these are caps are not coming out very well, but these are z cap. So vector equation, scalar equation, and constraint equation. Now we will work in Fourier space. Okay, so here what is a stationary state? Stationary state is u equal to 0, and I want to see the perturbation over u equal to 0. You are right, on some systems like in a pipe flow. So pipe flow there is a mean velocity profile. A pipe flow will have velocity profile like this. This is a linear system, rather this is a viscous solution. Now how, if we increase the pressure gradient, you expect at some point maybe the system may become unstable. So sometimes yeah, you use the mean flow, but for this problem u equal to 0 is my stationary solution, and I look for u not equal to 0, and theta is 0 is a stationary solution, theta not equal to 0 is a non-stationary solution for this problem. So you can see from here, if u equal to 0 and theta equal to 0, the whole equation is 0 equal to 0. Pressure also will be 0, pressure gradient will be 0. So 0 equal to 0, 0 equal to 0. So my u equal to 0, theta equal to 0 are solutions, and I know that for some temperature there is only conduction, no convection. So this is a stationary solution, stable solution. Now in one important idea in all this instability calculation is to use a Fourier mode. Okay. So I want to convert this PDEs, these are PDEs, to ODEs, and ODEs are much easier to solve, and then we look for some growing solution in ODEs. And one standard way to do convert PD to ODE is to use Fourier mode. No, the way we did, in fact all my previous exercise was to convert, use the Fourier mode to derive equations for the modes which are all ODEs. We just do it here. So just go to Fourier, that is why Fourier is very important. Now there are too many Fourier modes, so which one I am choosing? Now when you say, well, there are just too many Fourier modes, which is, when you do instability analysis, which one are you choosing? So my analysis will be general, but I will look for, when I do the condition, I look for the one which is most excitable, most unstable mode. Okay. So some people get excited very quickly, so we will find which is the mode which gets excited fastest, and that will set the criteria. So when I heat the fluid, not everything is excited in the at the onset itself. Some are getting excited later, but the one which is most unstable gets excited first, and that mode will come out of the calculation. So I will keep a general K, and we will look for one K which will be coming out first when the instability sets in. So for our calculation, so there are many different boundary conditions, but I will show you the simplest calculation. So we will use called free slip boundary condition. Okay. So and conducting walls. So this is free slip. So my walls are here. So in the horizontal direction I assume periodic. Remember Fourier is good for periodic, we showed that, but in the top and bottom I use a wall. Without that I can't set up convection. So if there is a wall, then you can see that my vertical velocity should be 0, right? At the wall, you hit the wall, you must be 0 velocity, otherwise you will break your head, So velocity must be 0 at the wall. Okay. So this means u dot n cap must be 0 for both top wall and bottom wall. But this is only on one component. What about other two components? And I think I did mention in the class that in realistic boundary condition for hard surfaces is that all the three components must become 0, but the calculation for that is quite complicated. we will not do it in this course. We will use a simpler boundary condition where this one stress free. So, for this wall, so this, let me set my axis, this is my x axis, z axis and y axis. So, if I go along z direction, my horizontal velocity must be 0. Is that okay? dux dz and duy dz is 0. So, how does stress come? I give the example, no. So, if the velocities are not same in two layers, then there is stress, but if velocities are same, there is no stress. If two runners are just running in the same direction, you tie them with a rope, no problem, they just run, but only when there is a difference in velocities, then there is a stress on the rope, no. So, this implies that horizontal velocities, when I go up near the wall, I get the same velocities. In fact, horizontal velocities are non-zero, in fact they will be like this. Okay, you see the arrows, they are equal near the wall. Okay, so this is stress free, and my conducting wall means temperature of the full plate must be constant, like copper plate, temperature is constant. So, temperature fluctuation on the plate will be 0. So, temperature at the top plate is T top, my notation is T like this, T top, okay. So, this small t is top, not time. So, T is constant, and so if you recall, T equal to T conduction plus theta. So, T top is same as T conduction. So, my theta must be 0. Okay. So, theta is 0 at the wall. So, these are conditions on the walls, and of course, the side walls periodic. It's a good assumption for. So, if the plates are, let us say 1 centimeter apart, but in the horizontal direction I have, let us say 20 centimeter, then it is a good assumption, periodic. Okay. At least the calculations are simpler. Okay, so let us calculate. This was done by Rayleigh first. Then the standard reference given book is Chandrasekhar's book, but my calculation is simpler than Chandrasekhar's book. So, that is what I will do. Okay. So, let me first do my calculation, then I will tell you the difference. So, I need to choose my velocity field. I am choosing a Fourier mode, no, which should satisfy this boundary condition. Now, if you have done PDEs, you choose your basis function. So, my ux, I want this ux, this one ux dz, partial ux partial z is 0. So, if I take partial ux, what will I get? I will get sin n pi z, and my, okay, I forgot to say, since I non dimensionalize this, what is the box height? 1. No, because my unit is d. So, in the unit of d, my box height is 1. I choose this to be z equal to 0 and this equal to z equal to 1. So, if I take the derivative, I get sin, and sin is 0 at both the walls. So, straightforward. So, at z equal to 0, z equal to 1, I need to satisfy these boundary conditions. Take for this one. Well, I should not take for everybody, but for this is ticked, right. Same thing for ui. What should I use for the z component for ui? Sin or cos? This one, partial ui partial z is 0. Again I should do sin, cos. I take the derivative, so it is again cos. Z function in z is cos, and this is exponential because periodic, e to the power I k y plus e to the power I k z z. What about uz? It is sin, because I want to make uz equal to 0 at the wall. So, sin. Okay. So, this will satisfy the boundary condition. That is the beauty of this. You can use sin cos to work with free slip basis function. If all the 3 components are 0, you cannot use sin cos. Okay, that is why free slip is easier. You have to use more complex basis function like Chebyshev. What about theta? What should I use for z direction? Sine, because I need 0. So, theta has same as this one, and along x and y I use this. Okay. Now, I use a hat here. So, what does hat? Hat is when it is a mixed basis, right? This is sine and this is exponential. So, I used a special name hat. Without hat is exponential for all directions, all 3 directions. Okay. I hope this point is clear. So, I put 2. So, this one, so this is hat, so I put hat everywhere. So, these are called free slip Fourier basis, but I can always convert this to exponential. So, what will I do for converting to exponential? I say e to the power I n pi z minus e to the power minus I n pi z divided by 2 I, and 2 will cancel. So, I. So, I had absorbed this I. So, what should I do? Theta hat by I. So, how do I convert from theta hat to normal Fourier basis function? So, you see, so theta hat by I. So, I write it here, theta hat by I will be theta of k vector, okay, is that fine? So, this is kx, ky, kz, this kx by kz, but I want exponential in all 3 directions. So, I have to divide by I have to absorb I along with theta hat to get theta, because I have this Cray-Haring requires Fourier. Okay, do not get mixed with mixed basis. Cray-Haring may have problems. So, we must get. So, I want to use Cray-Haring. So, I want to convert it to Fourier. Okay, but it is straightforward. This is a technology. Cos you do not need to do anything. For sine you need to divide by I, and of course, there is symmetry you have to keep. So, this has these 2 modes are connected by minus sign. Okay, so this bookkeeping has to be kept in mind. Okay, so that's why I had used sin x cos z. So, all the modes have certain relations among them, is imposed by the boundary condition. Okay, now I think I should want to go. So, now I put exponential, and I put without hat. Okay. So, this is Fourier, which we have done so far. So, this I am going to apply Cray-Haring on that. Okay. So, theta k. So, I take a Fourier mode. Of course, I understand that minus k. So, this has kx k by kz, but minus kz is related with kz. Okay. Now, I want to plug this in. So, we already know how to write the Fourier equation. I do not need to do the full algebra, just write down equation of the Fourier. So, this is my equation of Fourier. So, these terms you are familiar with, these. Viscous term is, so there is PR sitting in front with like nu k squared, no? The is theta k z hat. So, this is known, no? I mean, everybody is happy with this. So, theta r vector becomes theta k vector, not theta k z hat, z cap, theta is a scalar, sorry. So, from Rayleigh-Prandtl theta z cap, I get Rayleigh-Prandtl theta k z cap. So, here this d by dt is acting on uk of t. Okay, the u dot grad and all are this Fourier, there is nothing of grad. Okay, so this nonlinear term is off because convolution is off basically, because I linearize my system. So, I write down for theta. So, the term which has come is uz, and I have k dot uk is 0. I probably do not write it here, but yeah, k dot uk is 0. These are set of equations. After that, so I focus on single k. There are many k's, but I focus on single k. Okay, so let us do Cray-Haring. Okay, are you ready for Cray-Haring? So, this k has, so I fix the k, it is in the particular direction. So, here my k vector is here, but My only problem is that new term, buoyancy term. Otherwise, I know all the algebra I did in the last example is exactly same algebra. In fact, I don't have nonlinear term, it is straightforward. I need to worry about this buoyancy term. So, buoyancy term is z cap, which is in that direction. I need to resolve the z cap along E1 and E2 and E1, E2, E3, right. So you need to, when I use polar coordinate, then I need to resolve along the along the unit vectors. So what is z cap along E3? So this is zeta. So this is also zeta, 90 minus zeta, 90. So this zeta, right? Yeah, this zeta. Okay. So z cap. So just take the component like this, E3, and this is along E3 and this is along minus E2. Is that correct? This is E2. So that is so basically z cap is this plus this, right? Vector addition. So there is a component along minus E2 and component along E3, and this is related by cos and sin. So this is straightforward exactly. So along E2 it is minus sin zeta, right? This is minus sin zeta. This is sin zeta, and along E3 is cos zeta. So I take the component of my velocity field along these two, like exactly like what I did in the last example. So that will give me U1 and U2. But does the force have component along U1 or along E1? It has no component along E1, it has only along E2 and E3. So what does E3 component match with? So let's look at, okay. U dot is nonlinear term is off. So minus ik sigma plus Rayleigh Prandtl theta z cap plus Prandtl k squared uk. Okay, is that correct? This is what I'm writing slightly small, but sigma k. So my this has component along E1 and E2, along E3. So it has no component along E3. So if I take a dot product of this with E3, then only thing will give contribution is pressure. So pressure will balance with this one E3, which I told you in the linear example. Pressure will balance with the force in the z direction, force in E3 direction, not z, E3 direction. Okay. So I don't need to compute pressure. That is one interesting part. Pressure is off, gone, and pressure is matched by the this part. Okay. So now we are ready for writing for. I take this dot product with E1 and E2. So U1 has no component along force. U1 has no contribution coming from force. So in fact, it is a decaying equation, right? This is coming from here and this is coming from here. So U1 will decay in time, right? It is a decaying. U1 dot is minus U1. U2 gets contribution from here. So that E2 component, which was in the force. So this is the term, and this is coming from the force U2 component, and this coming from viscous tone. And theta dot is, well, theta dot is uz. Now I write uz as u dot z cap. Now z cap has component along U2 and E3. So E3 will give you 0. So U2 will give you this. Okay. So u dot z cap, that is it. You just compute and this. So I got 3 equations, and I don't need to worry about k dot uk is 0. So I need to solve these. So what does the first equation tell you? I look for asymptotic solution. Wait for some time. Okay, u1 will go to 0. What is the solution for this? u1 kt is exponential minus pr k square t, u1 k 0. So this goes to 0. So don't worry about it. In fact, my field becomes 2 dimensional because only u2 is present. u1 is 0. So if I look at this k vector, remember u2 is in the same plane as n cap. I mean n cap is in z direction, so I did not really tell you, but n cap is in z direction. Okay, so this x direction and this z direction. So my E2 is like this. So my velocity field has component along u2. The azimuthal component is 0. Azimuthal component is in that direction. Remember this one, that goes to 0, and this I can predict from here. Huh? Like in Chandrasekhar's book, he will work with stream function and he will not talk about this. Assumes 2D field, but here you can say that 2D will come by derivation. Now how do I solve this equation? Now I have two variables. Why u2k is a one variable, no? It is not I fix k. So I have two ordinary differential equations. So I can write them as a differential equation like this. This is my equation. Now my sin zeta is, what is sin zeta? This angle is zeta. So k perp by k. So this is I write it. So this is a matrix equation u2 theta. So matrix equation. So I solve a matrix equation. Okay. So these where we will start in the next class. Okay. So we stop. Thank you.